Hello, ladies and gentlemen. My name is Józef Kania. I am 70 years old. I am old. We are now in a makeshift studio set up by my daughter Kinga. And I will be honored to share with you some of my thoughts on physics. Physics in its broadest sense. I have been thinking about physics and its laws for many, many years. Well over a decade ago, one of my students asked me a simple question on Newton's first law of motion. Why is it that a lack of external force or a balanced force produces two different results? Either an object remains in motion at a constant speed and straight line, or it remains motionless. Please note the word "or". I think this was when my journey began. I began wondering why one cause produces two different effects. This made me think whether by any chance motion and motionlessness are both motion. If we assume that motionlessness is motion too, then we have one cause and one effect. Ladies and gentlemen, 50 years ago, I was happy to die for Newton, but not today. 40 years ago, I could die for Einstein, but not today. With all due respect to them. Not to mention Galileo, but let's not be such purists. Ladies and gentlemen, please note that the advancements in physics, and by advancements I mean investigating the universe more and more extensively, has led to forming more and more physical quantities. They were created as needed, so that we could keep refining our description of the world. Newton's contribution was the introduction of force. But what is it? Certainly, an elementary school definition, which explains that it is something that makes mass move or stay in motion, is absolutely fine. The only problem is that this is not a definition. A definition should be based on some fundamental units. The same is true for time. Could you please tell me, what is time? I don't mean a scientific kind of answer such as the fourth dimension of Einstein's space-time, because then my next question will be, what is that space-time? And we start going around in circles, meaning we multiply entities beyond necessity. I think in this case it would make sense to follow Mr. Occam's advice. His reasoning was this: if we can solve a problem in an easier way, or ideally the simplest way possible, we should do exactly that. Nowadays we call this method Occam's razor. In principle, it calls for shaving away all that is unnecessary, and what is left is a problem solution. I like this method. Of course, I agree that it's not always effective and doesn't apply to all the fields of science, but I would say that in physics it does make sense. Yet, physics has moved in the exact opposite direction, the direction of complexity. we keep creating still newer and more complicated theories such as the string theory or the holographic theory, not to mention the quantum or the gravity one, and so on. These theories are becoming more and more complex, making our description of the world more complicated too. So I ask myself a question. Can we make it simpler? Yes, we can. Physics. What is it? Generally speaking, it is a study of the reality that surrounds us. Every physicist, including me, would like to be able to describe the surrounding world. It's not so simple. For such a description, at a basic level, we need, let's say, 5 physical quantities. It's hard to define the world without distance, isn't it? Yes, it is. Without time, likewise. Without mass, agree. What about force? We need it too. Ideally, we would like to see momentum too. And, of course, energy. Well, that actually makes it 6. Ladies and gentlemen, these 6 physical quantities, subject to appropriate operations such as multiplication, division, etc., will give us all the other physical quantities. Distance divided by time results in velocity. You all know that. Force divided by mass is equal to acceleration, Newton's second law, and so on and so forth. I wondered if it would be possible to construct a model of the universe. Ideally, a factually correct model of the universe, without using these 6 quantities. We could potentially employ a smaller number of these units, which in fact is what physics is striving to do. How many? 4? Maybe 3. Not too bad. 2. Good idea. But it would be best to define the world with only one physical quantity. A single unit which would replace the 6 I have just listed, and perhaps even a few more. Any sane physicist will now say that it's impossible. But have you ever wondered how major breakthroughs have happened, at least so far? Namely, everyone knew that something was impossible to do, and so they didn't even bother trying. And then came someone who didn't know it was impossible and started looking for a solution. And they found it. I hope to be that someone. Please allow me to introduce you to the reality where meters, kilograms, seconds, joules, newtons are replaced with a single common physical quantity. Which one? It's simple. What is the fundamental property of our universe? Motion. Please note that there is no such thing as motionlessness. Motionlessness is also motion. If we move relative to Earth, Earth moves relative to the Sun moves within the galaxy, etc., then motionlessness doesn't exist. All there is motion. If we assume that the world is motion, then all these physical quantities which we have just mentioned, such as mass, space, time, energy, force, can be derived from that motion. It is not them that create motion, but it is motion that creates them. We may call it a theory of absolute relativity, if you will. Everything is relative. And this, as we know, has been scientifically proven since there is no absolute motionlessness. We move relative to Earth, Earth moves relative to the Sun, and so on and so forth. And so this motion continues. Based on that, I assumed that I could construct a model of the universe in which the fundamental quantities, expressed as numbers on axes, are motion. And what is the expression of motion? Velocity, of course. I have created a continuum in the form of a four-dimensional coordinate frame. X, Y, Z, U. All of the coordinates are perpendicular to each other and one another. Four perpendicular axes. I realize it's difficult to imagine that this vector is perpendicular to this one, and this one at the same time, with all four stemming from the same point. This is the hardest part of this theory to grasp. You need to imagine a four-dimensional continuum whose dimensions are velocities. In short, the mutually perpendicular x, y, z and u axes are velocity axes. To avoid confusing the velocity in my continuum with the velocity around us as we know it, I named my velocity vectors with the letter K and the Greek letter ni in subscript, kani. It's just so you know which physical quantity I'm referring to. Although, in essence, they are the same thing, they look different in my 4D coordinate system and different in the classical coordinate system, which is based on 3 dimensions, where the coordinates are distance, area, or volume. So please don't be surprised when you hear me using the term kani while referring to my 4D continuum, and the standard terms such as distance, velocity, acceleration, and other motion-related terms in reference to the classical physics, the one we are taught and are likely to study for some time yet. To recap, my continuum consists of 4 dimensions. Each of them is a velocity. This gives us a point which can be defined by 4 numbers that are velocities. If the point has a velocity in 4 directions, means it expands in these 4 directions. Or, from our 3-dimensional perspective, it simply swells. I agree it's not a pleasant experience, but we will address this issue a bit later. In fact, it's the very essence of the theory. If you're able to imagine a 4-dimensional continuum, I honestly admit it wasn't easy for me either. From now on, things will only be easier. I totally understand that imagining a point that swells in 4 directions at once requires some abstract thinking. But we need some basics to begin with. To reiterate, my assumption is that each and every point of my continuum expands in 4 mutually perpendicular directions. Of course, for now, the theory I'm introducing to you is based on just a single point. So for now, to me, the universe is a point. Its dimensions are not zero, but I will elaborate on that in due course. Still, for now, it's only a point. It's true that I find it challenging to expand the theory to n points, but it's just yet another thing to work out. Let's think about the implications of this assumption. First, I assume that the whole four-dimensional system is affine and isotropic. In other words, it preserves parallel relationships and uniformity in all directions. I then assume that there's a point in this four-dimensional space, and it's moving, let's say, in the direction x, like this. If so, then what is the product of the two remaining vectors of our three-dimensional space? Let's forget about the fourth dimension just now. What is the product of the two vectors which are perpendicular to the direction x motion? It's an area or a surface. Not necessarily a flat one, but it's some kind of surface. A surface area. The surface which is perpendicular to the direction of motion in my four-dimensional coordinate frame is called time. We now have the concept of time defined. If you try running an online search on time, you won't find a definition of time. Time simply is, because everyone assumes it exists. What's more, in most cases, science makes references to it. Please note that almost every formula involves time, but time isn't defined. So, what does it mean? It means that the formula contains something that, in fact, we don't understand or know nothing about. In my system, time has been defined as a product of two vectors perpendicular to the vector of motion. In other words, as a surface area. Having defined what time is in my system, now let's consider the product of time, or the surface area, and the velocity of the current direction of our motion. According to the geometry rules, the base area multiplied by the height results in a volume. We get a prism volume. A volume. In my coordinate system, this volume is referred to as distance. Now let's see if this works in the classical 3D coordinate system. If we multiply time by speed, don't we get distance? We do. So far, based on the velocity vectors, I have defined the concept of time and distance. Now, let's see what will be the product of our velocity vector, as we are still moving in the direction x, one of the two time vectors, because the surface area is made up of two, and the fourth vector, which is perpendicular to all of them. So, it's this one times either one of these two, times this one, which is the fourth coordinate. As we can see, the product is again a volume, just a different one, but the unit remains the same. It's still the third power. This unit, the product, in my coordinate frame is called a force. As you can see, by definition, there are two of these forces. It's either the product of the motion velocity, this time vector, and the fourth one, or the product of the motion velocity, the other time vector, and the fourth one. This means that my system accounts for two forces. Two only and no more. I realize it contradicts the classical 3D coordinate system, which lists more forces such as gravitational, electrostatic, magnetic, nuclear, strong, weak, and so on. There are several types of them, and these types meet the calculations requirements specific to our 3D coordinate system. However, in my 4D system, two forces suffice. These two replace all the others. What are these two forces? I can't say for sure yet, but it seems quite likely to me that the two forces that exist in my 4D system and are linked together with a single element are the electric force and the magnetic force. Please note the motion vector, one of the two time vectors, and the fourth vector, the motion vector, the other time vector, and the fourth vector. What links these two forces is the edge which they share at any given moment. That edge is the direction of motion. Now, what happens if the point not only is moving in some direction, but is also rotating around its movement axis? There are two types of motion here: linear and rotary. During the rotation, what happens to the forces which are affixed to the sides of the velocity vector? While rotating, they swap their places. One is where the other just was, and vice versa. Isn't it the same with the electromagnetic wave? The electric component is changing into the magnetic one. The magnetic component becomes the electric one. And they keep swapping like this at the speed of light, c. That's why I think the two forces in my 4D system may be the electric and the magnetic forces. I'm not saying this is certain, but it's possible. There is one more thing to note. In our classical 3D coordinate system, quantities such as length, area, and volume are expressed in different units. I mean, it's still a meter, but it's linear, square, or cubic. So, in fact, we differentiate length, area, and volume by using different units. However, in the 4D coordinate frame, they all are expressed with the same unit. Time, which is surface area, multiplied by velocity equals volume. This volume can be interpreted either as length, and that was my default assumption, or as surface area, still expressed in the same unit. Or it can be volume. When does this volume become length? When this dimension will be significantly bigger than the other two. Practically, motion is in one direction only, without any additional components. So this is length. The two remaining velocities in this and that direction aren't noticeable. They're there, so they're not equal to zero. It's important to note they are minuscule, but not zero. How small they can be, I will explain a bit later. Now, let's look again at these three velocity vectors. This one is still the direction of motion. If one of the two vectors that make up time isn't minuscule, but of significant enough magnitude, the unit, of course, stays the same. Then we no longer refer to length, but to surface area. If the magnitude of the third vector also becomes significant enough, then surface area becomes volume. To recap, in my coordinate system, the kani unit, written as capital K with subscripted Greek letter ni, denotes velocity. In short, it's meters per second or similar, but generally this is speed. So, if in the four-dimensional continuum this is the direction of motion, expressed as kani, then here is time, expressed as an area. This is volume, the product of three dimensions, which may as well be the length or area, as explained before. And this, stemming from the fourth dimension, is force, either of the two. So, that's the fundamental physical quantities defined. What else do we need to neatly describe the universe? Mass would be handy, wouldn't it? It would indeed. Ladies and gentlemen, here it is. When you multiply all the four vectors by one another, you have a kind of hypercube, or hypervolume. Please note, it's not a three-dimensional cuboid because there's an extra dimension in this formula, so the product is a hypercube. It may be a hypercube or a hypercuboid, it doesn't really matter. The point is that it's the fourth power. So we have a four-dimensional product, a hypercube. And this quantity is called mass. If we now move our hypercube in any direction, or in the classical 3D language, we put mass in motion by assigning certain velocity to it. Then the product of the hypercube and that velocity, again, in the classical system this is mass times speed, and in mine it's kani to the fifth power, is momentum. Now, let's take that mass and spin it in any way. I'm demonstrating it in our three-dimensional space, but you need to imagine this mass has four dimensions. While rotating, the side of this mass, in other words, the edge of the hypercube, moves over a certain area. The product of the mass and that surface area is energy. Please observe two more things. We now have a definition of time. But what do we call a unit which is the opposite of time? If time equals kani squared, then what's the opposite of that? It's frequency. If we assume that time is equal to the rotation time of an object, then what do we call a number of rotations within a unit of time? frequency. As you may remember, these two quantities are the exact opposites. So, if time in my continuum is kani squared, its opposite is 1 over kani squared, or kani to the second negative power. This is frequency. That makes the frequency unit defined. Lastly, let's talk about acceleration. Have you ever wondered when a moving object achieves its top instantaneous acceleration? When the object starts moving. After that, it only gains speed, but its acceleration declines. Based on this, we can say that in my system, acceleration is a unit which is the opposite of speed. In other words, acceleration is 1 over kani, or kani to the first negative power. We now have a range of basic physical quantities at our disposal, with appropriate operations on them such as multiplication, division, addition, etc. It's possible to derive all the other physical quantities. Here they are in the ascending order. Kani to the second negative power corresponds to frequency as we know it in the classical 3D system. Kani to the first negative power is the equivalent of acceleration. Kani, or kani, to the first power is velocity, the fundamental unit of my system. Kani squared is time. Kani cubed is distance or force, but also area and volume, as you may remember. Kani to the fourth power is mass. Kani to the fifth power is momentum. Kani to the sixth power is energy. Ladies and gentlemen, let's encapsulate my theory. The universe, which is the continuum I have proposed, is not in motion. The universe itself is motion. Please note the detail. It's not mass that moves in space or even force that makes mass move. They both, as well as all the other quantities, are generated or created by motion. So, the fundamental concept of my theory is motion itself. This assumption provides clear definitions of all the physical quantities in classical mechanics. I will discuss relativistic mechanics in due course. It's not a coincidence that this assumption makes it possible to derive all the classical mechanics formulae such as Newton's second law of motion. Acceleration equals force divided by mass, or speed defined as distance divided by time, or the kinetic energy formula, mv squared over 2, or work equals force times displacement. All these elementary formulae you may remember from your high school. Please note that with these simple assumptions, which I kept to the bare minimum, I didn't try to complicate the coordinate system. Unlike a classical approach to physics, I didn't introduce any additional physical quantities as and when needed. Let's recap. In my world, that is the four-dimensional kani continuum, all the physical quantities derive from 2, 3, or 4 basic quantities, all of which are velocities. When made into compounds, these basic quantities produce all the other quantities and relationships between them. This works with all the classical mechanics formulae and the electricity ones as well. See you in the next chapter, where I will talk about electricity. Thank you.